Hi, so in the previous video, and well, the previous two videos, we differentiated the r cosec function, so the inverse hyperbolic cosec function. So in this video, what we're going to do is progress from that and differentiate the arsech function, so the inverse hyperbolic sec function. So arsech is just the inverse function of the sec function, and so we're going to differentiate that. But before we do that, we're just going to do some graphical analysis to analyze whether we're going to have a positive gradient, negative gradient, a mixture of the both, positive and negative, in parts of the domain in which we can use the variable x. So let's just do some graphical analysis. So let's just start by plotting the graph y equals cosh of x. So cosh, by definition, is just a half of e to the x plus e to the negative x. So kind of like an average of the exponential function and the reflection in the y-axis of the exponential function. That's kind of what cosh is. So it looks kind of something like this. So kind of like the same shape as a quadratic, but it's not a quadratic. So that's what the cosh function looks like. But obviously this doesn't have a defined inverse because this is a many-to-one function. Just by using the horizontal line test, we've got two different points there for each line we do. So therefore, yeah, we don't have a defined inverse. We have to have an injective one-to-one function to have an inverse function. So we're going to restrict the domain, and we restrict the domain between 0 and infinity. So the domain is going to be x values between 0 up to infinity. Okay, so when we do that, then we can now draw a sketch of the sec function. So sec is just 1 over cosh. So y equals sec of x equals 1 over cosh of x. Okay, so drawing a sketch of this graph, well, I mean, if we just look at that point there, 1 over 1 is just going to be 1. So you've got a coordinate there. And then, as we said, we're restricting the domain, so we don't need to worry about the rest of these points there. We just only worried about the positive real axis. So as x increases, well, the value of cosh increases. So 1 divided by an increasing value of cosh, well, we're going to get smaller and smaller. And in fact, we're just going to do something like this. We're going to tend to we're going to tend to 0, starting from a sec value of 1. So that's what the graph looks like. And then if we just draw a y equals x line in there, so this is our y equals x line, we can draw like the reflected mirror image over that line y equals x in order to get the inverse function of sec. And that's going to look something like this. I'll do it in blue. So we're going to have a coordinate of 1, 0 there. We're going to have a graph which tends to 0, well, tends to infinity as x gets closer to 0, I should say. So yeah, this blue graph is going to be our arsech function. So let me just make this all a bit smaller. So yeah, what we will notice from that is that the arsech function kind of looks something like this. So this is y equals arsech of x. Okay, great. So we've got that graph there, and this is just tending to infinity. So what can we say then? Well, we know that this arsech graph, well, it clearly has negative gradients, doesn't it? So it clearly has a negative gradient for all positive values of x. So we'll bear this in mind when we actually use this method, the differentiation calculus method, to try and get this derivative. Okay, so let's begin then. So let's let y be equal to r sec of x. So what we can do then is apply the sec function to both sides. So therefore, sec y is going to be equal to x, because again, sech and arsech are inverse functions, so we just get the x on the right-hand side there. And then what can we do now? Well, we can differentiate both sides with respect to x. So differentiate that side with respect to x, and differentiate this side with respect to x. But of course, when you differentiate x with respect to x, you just get a number 1 there. So what do we get then? Well, we get that the derivative of sech of y with respect to x is just equal to the number 1. So let's just write that up there. So d by dx. Draw that arrow a bit neater. So d by dx of sech of y equals the number 1. So here we go. So we've got a function sech of a function y, but that y is obviously a function of x. So we can use the chain rule, and using our chain rule, we're going to get the derivative of sech of y with respect to y, and we multiply that by dy by dx. So again, that's just using the chain rule, and we've done lots of examples of this in previous videos, so you can just check out those previous videos if you're not sure how I've got that result there using the chain rule. And I'll just put chain rule in there to make it clear. Or you can call it implicit differentiation, as some people do as well. Okay, great. So now we've got d by dy of this sech y function. So we should know what the derivative of sech y is. So this is something that we did. And we know that, yeah, so from a previous video that I did, when you differentiate sech y, you should get the following. So you should get a answer like so. So you get an answer like so. So yeah, again, this is a result we got in a previous video. When you differentiate sech, you get negative tanh times by sech. So we're going to use that here. So therefore, we get negative tanh y. Sorry, let me just make that clear. Tanh y multiplied by sech y, and multiply that by dy by dx there. Okay, great. And this equals the number 1. Brilliant. So now we can divide both sides by negative tanh y sech y, and we will get dy by dx equals 1 over negative tanh y sech y. But I'm just going to move the minus sign on the denominator to the numerator. It doesn't matter where that minus sign goes. Move that up there. Okay, cool. So we know obviously that y equals arsech. So dy by dx is just the derivative of arsech of x with respect to x. So that's what we want. So therefore, d by dx of arsech of x is equal to negative 1 over, as we got down there, tanh y multiplied by sech y. Okay, great. So again, we're differentiating a function of x. We get a function of a function of y as a solution, but obviously we don't want this. So we want to eliminate this function of y. Well, we know that sech of y is x, so we can just plug that in. So we know that sech of y equals x. So therefore, this is going to be negative 1 over x times tanh y. What else do we know? Well, we know one of these identities, these hyperbolic identities, and we can derive this hyperbolic identity as so. So we know that cosh squared take away sinh squared is identical to 1. Sorry, let me just put the variable y inside there. Sinh squared of y equals 1. So we know that identity. If we divide everything by cosh squared, we get this. So 1 minus tanh squared y equals sech squared y. rearranging to make tanh the subject to the formula. So what you're going to get is you'll get tanh of y equals the square root of 1 and then minus sec squared of y. Okay, so we get that there. So what we can therefore do, because we know sec of y is just x, we can just rewrite that as 1 minus x squared, like so. Okay, great. So what we're going to get then is we're going to get a negative 1 on the top multiplied by x times the square root of 1 minus x. And so by using this method, we get this derivative here. So we've got to go back to the graphical analysis and check whether this is indeed less than 0, because we need this function to be less than 0 for all x values in our domain. So if we go back here, again, we've got this y equals arsech function, and we can see the gradient is negative. So we know for a fact, so fact d by dx of arsech of x is less than 0 for all x values in our domain. And as you can see, our domain actually goes from 0 to 1. So for all x values in our domain, 0 to 1. And that's because this coordinate there is just 1, 0. And as x tends to 0 from the positive side, the arsech function tends to infinity. So this is the fact we've got to bear in mind. So when we plug in any x value between 0 and 1, is it true that this function here is always negative? Well, let's think about it. So on the top, we've got a negative 1. And let's just put in the rest of this denominator here. So 1 minus x squared there. So we've got a negative 1 on the top. So this is indeed a negative number on the top. Okay. We've got an x there. This is a positive number. Okay. We want to get a negative number, don't we? So therefore, it has to be true that this number in there is a positive number. So let's think about it. Well, x is a positive number between 0 and 1, isn't it? So it's a positive number between 0 and 1, and we're squaring that number. So when you square a number between 0 and 1, well, you get a number between 0 and 1. So therefore, this x squared is between 0 and 1. And when you take away, well, when you do 1, take away a number between 0 and 1, you get a number between 0 and 1. So therefore, this entire thing inside the square root is between 0 and 1. Square root of a positive number is a positive number, obviously, and it exists in the real numbers. So we've got a positive number there. So therefore, this works. Yeah, so it's perfectly reasonable and it's perfectly fine for us to state this, that the derivative, I'll do it in black ink. So the derivative of arsech of x is equal to negative 1 over x times the square root of 1 minus x squared. And that's because x is in this part of the domain where x is between 0 and 1. And this actually does work. Yeah, so therefore what we can deduce from that is indeed this formula is true, this result is true, and that differentiating arsech gives us negative 1 over x times the square root of 1 minus x squared.